Yo, what's up everyone? Today we're going to be doing the 2021 USNCO local exam thermodynamics section. So this is from questions 19 through 24. Let's get started with question 19. Burning 48 grams of graphite in excess oxygen under standard conditions releases 1,574 kilojoules of heat. What is the standard enthalpy of formation of carbon dioxide? So we're told that burning graphite in excess oxygen releases CO2 releases 1,574 kilojoules of heat. The thing is, this represents 48 grams of graphite. When we want the enthalpy of formation, the reaction that we want to find the enthalpy of is going to be the reaction that forms only 1 mole of our compound. So the reaction that we want is just 1 mole of this. So we want to take this and we want to multiply it by 1/4 to get our enthalpy of formation. So if we take 1,574, we divide that by 4, that gets you 394 kilojoules per mole. Now, the negative comes in because we're releasing 1,574 kilojoules for 4 moles. So if you're releasing energy, then that means your system loses energy. Therefore, its change is going to be a negative number. Again, it's 1/4 of the value that we're given because we have 48 grams of graphite, which represents 4 moles, but we want 1 mole. And again, it's negative because you release that heat. So the answer is C. Let's go to question 20. Two metal samples labeled A and B absorb the same amount of heat. Sample A has a mass of 10 grams and its temperature increases by 38 degrees Celsius. Sample B has a mass of 20 grams and its temperature increases by 23 degrees Celsius. Which sample has the greater specific heat capacity? All right. Remember, the formula for heat is equal to mc delta T, where m is your mass, c is your specific heat capacity, and delta T is your change in temperature. We know that 10 grams times our specific heat capacity, let's call it C1, times 38 degrees Celsius is going to be equal to 20 grams times C2 times 23 degrees Celsius. Now, these are equal because we're told that in the problem. We're told that they absorb the same amount of heat. So what we want to do now is compare C1 and C2. We know that 380 times C1 is equal to 460 times C2, which means that C1 is greater than C2. So the sample A has a higher specific heat capacity than sample 2. So our answer is A. Let's go to question 21. A reaction has a change in entropy of a positive change in entropy and a delta H that's also positive. Which statement about the reaction must be correct? All right, A, if carried out in a well-insulated container, the temperature of the reaction mixture will decrease. In order to look at what happens to the temperature, we have to look at enthalpy. Since our enthalpy is positive, then that means our products have more energy than our reactants, so the system absorbs heat. It takes in energy. If it takes in heat, then that means it has to get that heat from the surroundings, which means that the temperature of the surroundings will decrease. So A does make sense. Let's go through the rest to make sure that they're wrong. B, it will occur spontaneously at 298 Kelvin and 1 atmosphere of pressure. To find out whether or not it happens spontaneously, we have to look at Gibbs free energy, which has this formula. It's delta H minus T delta S, the entropy. And so we're told that our entropy is positive and our enthalpy is also positive. Depending on the magnitudes of delta H, delta S, and temperature, delta G could be positive or negative. If delta G were positive, then that would be non-spontaneous. If it was negative, then it would be spontaneous. But in this case, we don't really know whether or not it's going to be spontaneous or not, because we don't really know the magnitudes of delta S and delta H. So B can't be correct. It could be correct, but it isn't necessarily correct. Okay, let's take a look at C. As the temperature is raised, your equilibrium constant for this reaction decreases. To find out whether or not that's true, we need to look at a certain formula. So delta G is equal to minus RT natural log of K. Delta G is your Gibbs free energy, R is your gas constant, T is your temperature, and K is your equilibrium constant. To more understand the relationship between your K and your temperature, we can rearrange to have K on one side. So K comes out to e to the minus delta G over RT. And from this this form here, you can see a bit more easier the relationship between temperature and your equilibrium constant. As you increase your temperature, your exponent here becomes smaller. And when your exponent here becomes smaller, your K value becomes bigger. So as your temperature increases, your equilibrium constant also increases. So that's not what we have in C, so C can't be right. And D, the reaction has more moles of product than it has moles of reactants. Now, I guess this could explain why our change in entropy is positive, but your entropy could be positive, your change in entropy could be positive from other factors like a phase change. So although this could be the case, it's not necessarily the case. It's not necessarily, it must not always be correct. So D can't be the right answer. Therefore, A is the answer for 21. Let's go to 22. What is the boiling point of water in a pressure cooker with a pressure of 2 atmospheres? And we're told that the enthalpy of vaporization of water is 40.7 kilojoules per mole. The fact that you have an enthalpy of vaporization, 2 sets of pressures, and 2 sets of temperatures means that you're going to be using the Clausius-Clapeyron equation. The Clausius-Clapeyron equation relates temperatures with different pressures as long as you're given the enthalpy of vaporization. So the Clausius-Clapeyron equation tells us that the natural log of pressure 2 over pressure 1 is equal to the negative enthalpy of vaporization over R times 1 over temperature 2 minus 1 over temperature 1. So we're going to need 2 sets of temperatures and pressures. How do we find those? Well, let's say the first set of temperature and pressure is just normal boiling point. At normal boiling point, you are at 1 atmosphere and you are at 100 degrees Celsius, which is 373 Kelvin. Let's say our second set of pressures and temperatures is going to be the one where it's at 2 atmospheres. What we're trying to find is the temperature at which this boils. What we're trying to find is X. So we can set up our equation with the information that we know. So 2 atmospheres over 1 atmosphere equals to minus enthalpy of vaporization. The gas constant that you're going to end up using, your R here, has a unit of joules. So you're going to want to turn your kilojoules into joules, so 40,700 kilojoules per mole, joules per mole, over R is 8.3145, plus some other units and stuff. And then it's multiplied by 1 over T2 minus 1 over T1. I'll just write that here. So 1 over T2, T2 is what we're trying to find, and 1 over 373 Kelvin. And all you have to do from here is solve for X. And when you solve for X, X comes out to 393 Kelvin, which if you want to convert that into Celsius, all you have to do is subtract 273, and that gets you 120, it rounds to 121 if you actually do out the calculation, degrees Celsius. So our answer is B. All right, let's go to question 23. The gas phase bromination of propene has a standard enthalpy of reaction of negative 122.5 kilojoules per mole, and we're given the reaction here. We're also given a couple of substances and their standard enthalpies of formation, and we're asked what is the standard enthalpy of formation of C3H6Br2 gas. Whenever you're dealing with enthalpy of formation, it always helps to write out the reaction that you're dealing with. So we're trying to form 1 mole of C3H6Br2 gas. So we're going to need 3 carbons in its solid form. That's the standard state of carbon. We have 3 H2s, that's the standard state of hydrogen. And we're also going to have 1 diatomic bromine, and that's going to be in its liquid state. So bromine is in its liquid state in standard state, and this all forms C3H6Br2 gas. And we're trying to find out what is the enthalpy of this reaction. All right, we have a couple reactions here. The first one is the first one that we're given. It's C3H6 gas plus Br2 gas form C3H6Br2 gas. We're also given two others, and they're not as obvious. The fact that you have an enthalpy of formation means that you have reactions associated with all of these. So in the case of C3H6, it's going to be that 3 carbon solids plus 3 H2 gases are forming C3H6 gas, and this has a change in enthalpy of 20.4 kilojoules per mole. The last one that you're given is the one for bromine. Now, bromine is naturally in its liquid state in standard form, so turning bromine liquid into bromine gas takes 30.9 kilojoules of energy per mole. All right, essentially from here, the entire question is just an exercise of Hess's law. If you add up the the bottom two reactions here, you'll end up getting the reactant side of your final reaction. So if we add them up, 3 carbon solids plus 3 H2 gas plus bromine to liquid produces C3H6 gas plus Br2 gas. And Hess's law tells us that we can just add up the change in enthalpy. So this has a change in enthalpy, standard change in enthalpy of 51.3 kilojoules per mole. All right, now that we have the reactant side done, we need to figure out how to get the right product. What you can do is you can add up the reaction that we were given with the reaction that we just found. And what ends up happening is that the reactants from this reaction cancel out the products from this reaction, and you're left with the C3H6 that you want, C3H6Br2 gas. So if you add up the top reaction and the one that we just have, you'll get the reaction that we need, which is this one over here. So all that's left to do is add up their enthalpies. So one has an enthalpy of 51.3 kilojoules per mole, and the other one has an enthalpy of negative 122.5 kilojoules per mole, and this all comes out to negative 71.2 kilojoules per mole. And that's your answer. So that's your standard enthalpy of formation of C3H6Br2 gas. Again, this whole thing was basically an exercise of Hess's law. And yeah, let's go to our last question, 24. Titanium has a normal melting point of 1668 degrees Celsius and a molar enthalpy of fusion of 14.15 kilojoules per mole. The standard molar enthalpy of liquid titanium is 97.53 joules per mole per Kelvin at 1668 degrees Celsius. What is the standard molar entropy of solid titanium at this temperature? All right, there's a lot here, but let's start off with our enthalpy of fusion. Enthalpy of fusion is the amount of energy it takes to turn 1 mole of a solid into 1 mole of a liquid. So titanium going from its solid form to its liquid form would require 1415 kilojoules per mole of energy. The other thing that we know is the molar entropy, that should say entropy, entropy of liquid titanium. So this has a molar entropy of 97.53 joules per mole times Kelvin. And now that's all the information that we're given. What we need to know now is the fact that this is a reversible reaction. Titanium goes from a solid to a liquid, and if you lower the temperature, the liquid will turn right back into a solid. Since this is a reversible reaction, our change in entropy is going to be equal to our heat over the temperature. And so what is our heat? What is our temperature? Well, the heat is our enthalpy of fusion. It's 14,150 joules per mole, and our temperature is just 1668 degrees Celsius, which is 1941 Kelvin. So what that means is that our delta S is equal to 7.29 joules per mole times Kelvin. So if we take the entropy of liquid titanium and we subtract it from solid titanium, liquid minus solid, that'll come out to 7.29 joules per mole times Kelvin. And we know the entropy of our liquid titanium, it's 97.53. So 97.53, I'm not going to put the units, equals 7.29. And all you have to do now is solve for your solid entropy, and that comes out to 90.24 joules per mole times Kelvin. So our answer is answer choice B. That's the answer for 24, and that was the entire section. I hope you were able to learn something. I hope this was helpful, and I hope to see you later. Thank you.